Welcome to today's Essential Reliability webinar, take 3. Still trying to figure out which buttons to push after a long set of holidays being away. This is Fred Schenkelberg, and I want to talk about what do you do when you have an accelerated life test that really should be done or is desired to be done or is required to be done, yet it's going to take too long to get reasonable results. And I should have really changed the name of this to too long of an ALT, because I know many of you, and myself included, has designed and run accelerated life tests that may take 4 or 6 months to actually get reasonable results. Now, that's not what I mean by a long ALT. It's an ALT that all parties agreed they needed the results. We had a new product coming out, and a major customer said, we want to know if this is going to work or not, and we're willing to wait until the results come in. And there weren't really much of any options to speed the test up that we knew of at that time. Later, we did figure out some other clever ways to go about doing it. But so that we outlined what the test would take to accomplish, and the customer was saying, we'll wait for the results. And they did. And then they ended up buying the product. The product was going to last well in excess of what they were, minimum requirements they had. That wasn't a problem. The real issue is that if the design of the test and our ability to do the acceleration required us to run the test for, say, 6 months, yet we needed to make a decision in, say, 2 weeks or in a month. That's where the conflict comes in, right? Is that in order to run an adequate test to demonstrate or show or measure the longevity of some product for some specific failure mechanism, that sometimes it takes us longer to get that answer than the time we have available. Now, there's other issues with that, is not able to get as precise as we want and not enough samples and stuff like that. But I'm not going to really talk about that too much today. It's more when your option to run an actual accelerated life test is going to take too long for the decision that needs to be made based on that information. And so there is the conflict I want to talk about today. Now, when I first ran into this, there was development time, and I think every trade journal article I saw at the time was, and I think they still do it today, is that development cycles are getting shorter and shorter. The time it takes to crank out a new product version, it used to be a year, then it was every 6 months, now it's every 3 months, and in some products, it's almost continuous. The development time is one criteria, and one of the major decisions in developing a product, and especially when it has some new element or material or process or something in it that we just don't know enough about, is the question comes up is, will this last long enough? Now, the very first time I heard about accelerated testing, I was asked to show that this product would last for 20 years. And I said, well, if I have a bunch of samples and have 20 years, I can give you a reasonable answer. It still won't be perfect, yet it'll take 20 years. And they said, no, you got to do it faster than that. So then I went to the library and learned about how do you accelerate time. And I've been hooked ever since. That was really my first intro into reliability engineering. When the product only has 6 months before we have to make a decision, is it ready to ship or not? Then you only have 6 months. And oftentimes that decision is, do we go to production or not? And we might have a little bit of room around that to really hone in on the decision. Oftentimes, though, if the development cycle is 6 months, we might only have 3 months by the time we get samples and the design and materials are locked down and all these other pieces go into it. More often, I see the better companies saying, we want to develop this technology or this material or this component or whatever, and we'll do it offline. we'll understand it and characterize it before we decide to even put it into a product. That's getting more and more rare, in my opinion, in the companies I've been working with, is that they say, oh, we want to use this widget. We don't know anything about it. Can you show that it's suitable for the duration we want it to run? Well, what's your timeline? Well, we're already 2 months into our 6-month cycle. So you get, 3 months before we need to know. And sometimes we can run a test that will give an adequate answer. And many times that time crunch is really a showstopper for getting a reasonable answer using traditional or classic accelerated life testing with a given model. So that's really a problem. Now, some durations, I've run some accelerated tests that really only take a few minutes. It's something that's used, power cycled once a year, for example. Well, I can do 20 power cycles in a day with plenty of time for it all to cool down. And we have evidence, at least with that one sample, hopefully many more samples, that we're good for power cycling related failure mechanisms for that product. On the other hand, the accelerated testing, I once was consulted with a team that was doing a low orbit satellite. And it was like every 30 minutes, this thing was around the Earth and it would go from the shadow to the sun side. And it was more severe conditions than I could replicate reasonably on Earth for the amount of thermal shock this thing saw in the rate and the amount of temperature change that was occurring. And so at that point, it was just technically, no, we really can't do that. It would take me a lot longer to find out if this thermal cycling is going to cause you an issue than if you just put one up in space and see how it's going. Of course, they wanted an answer near immediately. So we just didn't run the accelerated test. They took a handful of other ideas, which we'll talk about today, to see if it would work for them. So hopefully that expresses in one way or the other the conflict that exists. And sometimes our ability to cheat time, it just isn't good enough. And then what do you do? The options, and when oftentimes I look at, if there's a conflict or a dilemma of some sort, what are our options? Well, I often start at the extremes. Right. Well, let's just delay the program in launch of the product or the decision that needs to be made until we can finish the test. If it's really important, we'll wait. Yet that has costs. Many of you are going, well, that won't fly. That's not going to happen. On the other extreme is, well, let's just ignore that information from the accelerated tests and not run one at all. If it's not feasible for us to get test results by the time you need a decision, well, let's not even try and waste all that time and money and effort and resources and samples and everything else and get a partial answer, which will be at best less than useful. Let's avoid all that and just make an engineering judgment call or try something else, or just don't do it. Good luck with your decision. Some people can't sleep at night, and if they know there is a way to get better information, but they don't want to wait for it to occur, that I think leads to ulcers for some people. But the idea is that there's that conflict. And in reliability engineering, this is just one of them. Our other one that we see more often is on sample size. But let's talk about this duration thing. So here's a question that hopefully has come up in your mind already. So one option is, push the limits of our technology and our understanding of the failure mechanisms and everything else. And let's just turn the temperature up. I've heard that a number of times. Let's just cycle it faster or use higher temperatures or do whatever. So what happens if we just do that? If we just crank up the stress and run the test faster? I know some of you have heard this question more than once. So what do what do we lose? What happens if we just push it? Yeah, exactly right, Kevin. Is, if like with that very first one I ran is we were running the temperatures at the high end of we did three different temperatures. The high end was pretty close to the softening point of the polymers, and it was a polymer product that we're evaluating. And so it was physically changing. So if we added another 20, 30 degrees Celsius, the thing would have melted. It's not behaving at all in the same material phase that it would be in use conditions. So extrapolating results when something's melting to when it's at room temperature and perfectly solid, as solid as polymers get, just doesn't make any physical sense whatsoever. And it might be possible. Some materials, when their phase change, maintain a lot of their properties. But by and large, that's another whole project to figure it out. Yeah. And Kenneth is chiming in on it. And Carl's mentioned in other areas is get more errors, right? We're already pushing the stresses in order to accelerate a failure mechanism. And unless we have a really good characterization and understanding of how those two things, how the relationship between stress and how fast it leads to a failure is really well known, we are taking a gamble, right? And remember, we're also extrapolating the results out to whatever piece of it is. So a small variation in our testing algorithm and model can, when extrapolated, really create a large error. And those are hard to detect. You really got to count on the physics and chemistry and the understanding to minimize those errors. So by and large, we lose, and I hate to say it, but confidence that the results are meaningful, right? And I've heard somebody argue this, well, just it's a 10 degrees Celsius, increase will cut the test time in half. All right. Based on what? Oh, we just assumed an activation energy. All right. Well, there's no evidence one way or the other that that's the activation energy. And what about phase changes? If your failure mechanism has to do with moisture, like a corrosion process, right? What happens when your water freezes? Doesn't that kind of stop that whole process or really, really slow it down at a rate that's much different than when it's just merely cold? Or vice versa. What if it goes to steam? Does that accelerate the corrosion at the same rate or at a different rate? Do we really know? And so the whole concept here is when we're asked to set up an accelerated test, we need to know quite a bit about the failure mechanism involved in order to design a test that will give us meaningful results. Hopefully, this is not new information to you, right? It's one of the reasons I really don't like standards is they don't usually explain where the limits are, what are the rationale behind it, what are the mechanisms really at play, what's the chemical or physical process. And trust me, you do it 100 cycles, you do it for 100 hours, then you're good. Well, good for what is what often is missing from standards that I've seen. So let's assume that we're trying to do the right thing and understand the mechanism and create a test that will give us meaningful results that will reflect what happens in reality to our best of our ability. Just ignoring that and just adding more stress until it fails, very likely, many of you already noticed, is that you'll get a mechanism that occurs that has nothing to do with the ones that would occur in real time. And so we get that. Then the point is, then what do you do, right? So and I think I'm going to repeat a little bit here, but the idea is, I think this is all stuff I just talked about. I guess I got ahead of myself a little bit. Is it's not magic. Is gravity doesn't care, right? It's going to apply itself, and you're going to, if you fall off a step ladder, you're probably going to fall down in the direction the gravity is going to take you, independent of how much you desire that not to happen. And that, for people that don't understand the mechanics or the mechanisms of failure, of how failures work and don't work, that can be difficult for them to understand. Well, just throw it in the chamber, right? Just, crank up the temperature, do this, that, the other thing. And like, well, it's a test. I get that. And we're going to run stresses on it. I get that. But if I take, instead of a ball peen hammer, a small, half a kilogram size hammer, and replace it with a 4-ton hammer, yeah, I can apply a whole lot more stress. I'll probably get a different failure mechanism though, if I try applying that load to something and try to extrapolate it back. It's probably not going to happen. The other thing that happens is that, especially if you're doing a one from scratch, you don't have a good model, you're using 3 or more stress levels. If the higher stresses just fall out because you got a different mechanism, now you have even less information in order to make a model with. So hello, lots of errors there. So lots of things to come into play. Yeah, Angie's asking the question, does HALT come into play? It does. Remember that HALT does not have the capability to tell you, will it last for 20 years, for example, is that very first project I came up with or was asked to do, was they wanted to know if this cable in this application would survive and operate as expected for 20 years. And we knew the failure mechanism, and it was accelerated. It was a chemical process. The polymers would oxidize, and we used the Arrhenius equation with temperature to accelerate it. And we had lots and lots of previous testing done, that and field data that corroborated it. Our testing was a little bit, gave us a lower projection of its lifetime than what it actually did. And that's a subject for a whole different technical paper and webinar and stuff, how that turned out. It turned, well, short story is that the oxidation actually limited the amount of oxygen that was allowed to get into the bulk of the material. It kind of created a barriers. Think of it as one of those beneficial corrosion things. I think copper does that, right? It gets this copper oxide, which preserves the bulk of the copper. It just creates a layer that prohibits oxygen from continuing the corrosion, for example. And so we were able to adjust for that phenomena once we discovered exactly what was going on, and even got a more accurate test. But the idea is that we really understood the failure mechanism. And we also knew that this polymer has a melt point. And then somewhere prior to that, 10 to 20, sometimes 40 degrees Celsius lower than the melt point, it would have a softening point, which then parts of it were melted and parts of it weren't. It softened. So we knew it was going to behave differently at those points. So we tried to avoid all those things. Now, HALT is a great way to figure out what fails. So if I keep adding stresses to it, step stress, and keep adding stresses to it, for example, if I'm using just a static load on a shelf, for example, and I have I'm getting ready to build a shelf in my house. And one of the questions is, how far apart do you put the uprights, the supports for this thing? And how strong is your wood that's going to be on that shelf? Well, I could do a static test that gives me the yield. If I consider a failure that bows by more than a 1/4 inch, I could probably work out a pretty decent, simple test to figure that out. Now, HALT would be, I'm going to keep increasing the loads until the shelf fails. Now, it might, if I don't know how it's failing or what are the ways it can fail and what are the things I should do to mitigate that, halt's a great test. It allows me to figure out, is it the hinges? Is it the wood itself in the middle? Is it, does it deform and not an elastic deformation and it stays bowed and that doesn't make a very nice looking shelf? Is the wood crack on the bottom, or is it compress on the top and buckle? Do the shelf pins slip away, or do they deform in their sockets that they're in, or some other phenomena? But once I know what the failure mechanism is that I learn in halt, I can either do design changes to mitigate it, or I can run an accelerated test to say, well, what exactly is this mechanism? How long will these things last? Especially if it's deformation, so on. And Carl, I often call HALT the second worst four-letter acronym. And those that know me very well probably already know what the top worst four-letter acronym in our business is. The idea, though, is HALT and ALT serve different purposes. If we want to know how long this will last, ALT is a way to go, or life testing is a way to go. If we want to know what fails, what's likely to fail, then HALT is the way to go. And I haven't seen any evidence yet. I've seen plenty of claims, but no evidence and no confirmation that anybody knows how to convert HALT into a life test that actually gives you a probability of duration over time. So, but I'm still open to it. It'd be really nice, yet I don't think we have quite figured out how to trick nature into shortening times to failure in a meaningful way, just because we want to. So we end up with these decisions. And so part of the way I think about how do we get around this, or how do we solve this problem is, well, how well do you need to know this answer? You know, like this one company wanted to know, will it survive in our environment for 20 years? And it was a seasonal device that every winter would turn on and create heat and do stuff like that. And we knew it oxidized, and they wanted to know, will that process degrade its capability to create enough heat to a point where it doesn't function for us? And it's a great decision. And they said it was very important for them because we're going to spend millions of dollars installing your product. And if it doesn't last for 20 years, it's very cost prohibitive to replace it. It was buried in concrete and bridges. And so it was, I think, close to a $30 or $40 million question for them. And they wanted to know an answer, and they were willing to wait. It was that important of a decision to them. Now, if it's just somebody that says, well, I really hope it lasts long enough, yet there's no financial penalty. If it doesn't, it's outside the warranty period. It's not inside the customer satisfaction realm. It's just something that we set a target arbitrarily and we'd like it to last. At some point, you got to push back on that. Is this decision really necessary? Are we good enough with the information we have? Do I need to run a test when I could use field data instead? And how important is the decision is a key piece to keep in mind. If it really is a big deal, yeah, then we got to do something about it. And hence some of our dilemma, right? Our trade-offs. One of the things I've run into, and I really hope you don't consider this as a part of the possibility, is run the test anyway. And after 2 weeks of, say, a 6-month test, see how your results are. And even if you had lots of samples and everything else, and you're looking for a wear out mechanisms that would take in the field 20 years to occur, or you hope longer, and you have say a 6-month design test with the temperatures and everything else, was when you expect less than 1% of your samples to exhibit some failures, if it's going to exist at all, looking at your results after 2 weeks is pretty much downright meaningless. The probability of seeing a failure, let's say I had a couple hundred samples, might be in the absolute near invisible or impossible, or lots and lots of zeros before you get to a chance that it would fail. So even if I had a couple 100,000 samples, which is probably not practical, the chance of seeing a failure that indicates it's not going to last is near nil. Of course, we're not going to see any failures. If the test is run properly, if you understood your failure mechanisms, all those kinds of stuff. Then it goes back to what Carl mentioned, is that, well, it increases the error. If I'm at 15 nines out on the tail of this distribution, I really hesitate to say we know enough to know where the average time to failure is. Excuse me. So part of the problems is if we do a partial, we get less than partial answers. We get really misleading answers pretty quick. And then we have to get into statistics to try to explain it to somebody. But let's take a look at what else can we do. So let's do a couple of them. I'm getting ahead of myself a little bit in the slides. And part of the issues is that I've talked to way too many people about setting up tests to get them a good answer for an important decision. And I've heard all of these, and I'm sure many of you will have seen or heard these also. Well, just get another chamber that goes higher in temperature. We can rent one for $100 a day, and we can crank it up to 400 C, and it'll go faster, right? Yeah, it'll catch on fire probably, or melt. And we will not get any useful information. The phase changes matter. Somebody wanted to do a freeze thaw test, and it's like, it's not cranking up the heat. It was, well, let's make the ice colder. So we'll go to minus 40 degrees and we'll go to plus 40 degrees. This is a freeze thaw test. What we're looking at is thermal expansion of this moisture from water to ice, and it expands and creates cracks and compromises seals and does all kinds of stuff like that. It's a mechanical movement. Ice at minus 10 to minus 40 is still not that different in size. I think it actually shrinks a little bit. What we're after is that movement. And patiently trying to explain this to somebody that colder ice is not going to accelerate this test. It's actually going to slow it down, because from going from minus 10 to minus 40 takes a lot of energy for this to occur. It takes time. In going the opposite direction, if going from 10 degrees to 40 degrees Celsius, it also takes energy and a lot of time. And for what? It's not a thermal cycle test. If we really are dealing with something that's just not going to do a phase change, and it goes from minus 40 to plus 40, that's 80 degrees Celsius swing. That's great. But what does it get us? And when we're doing a freeze thaw test, not a whole lot. So understanding how just adding more stress to something, and what are the limits? And there's always a limit, whether it's temperature or heat or the chemistry involved, or phase changes is my favorite one. All of these different things we can do, yet the opportunity to actually get meaningful results is almost nil. So careful how you go if you just crank it up, as so many of my clients have said at one point or another. The other alternative is, well, call your vendor. Let's say you're getting a power supply, or like in the case I was running, it was one of the first things we did is we called the polymer vendor and said, well, how long will this last? And their answer was interesting, is the way I phrased it, was they said, well, if you leave it in pellet form in your warehouse and it's climate and humidity controlled, that polymer will retain its ability to be extruded for at least 10 years. Okay. Which is understandable because they care about shelf life and how much you're buying and how much you're going to use and how long they can have it in their warehouses and all those kinds of things. They never actually looked at it for it oxidizing and changing its ability to expand and contract when it's slightly aged. They had no idea that that's why we were using their product. That's how we did it. We put additives in it so that it would have this electrical property. And they said, well, you've changed it. You've put other stuff in it. So, and you've extruded it, and the shape and the dimensions and the temperature of your extrusion process and all that make it something that we can't make any claims about. But if you looked at their data sheet, it said it's good for 10 years. I mean, it didn't say that in pellet form before you extruded it, it was good for 10 years. It just said it was good for 10 years. And you had to do a bit of digging and understanding is what did they really mean by that? You know, Joanne, yeah, vendors are optimistic. I remember one I was talking to across the table with a client, and I said, you know, how do you know it's going to fail? Oh, we've never seen any failures ever. So we're very confident it will last for as long or longer than you ever need it. I said, well, I want it to last 100 years. Are you okay with that? Oh, yeah, it'd be fine. And I said, so what evidence do you have at all? And it goes, oh, we put it in a chamber for a few hours. It's good. Oh my God, this is crazy. I had a accelerated test. It was for a new socket that had some new technology built into it. And this is years and years ago. And one of the issues was is they used a layer of metallization called gold flash. Now, many of you that deal with electronics or connectors and sockets and stuff like that probably cringe when you hear gold flash. And I don't know where the state of the art is these days, but when I was involved at that time, getting flat gold layer on a surface without any holes and resilient enough that with any thermal cycling, it wouldn't create openings. And usually that meant it would be open to corrosion. Was exceedingly difficult. So we wanted to do an accelerated test to see if this socket would fail due to corrosion. And this coating would fail due to corrosion. So the vendor said, all right, we understand. We'll work with you to design the test. They were part and parcel to the development of it, the operation of it, the testing of it, and everything else. And they sent us 30 samples. They claimed were randomly selected from their available material, which you and I all know that they didn't go out to the 10 million units they had and truly randomly selected. They took 30 that were convenient. We ran the test. 28 of the 30 failed in the duration of the test, and we were expecting none to fail. And if it met the requirements that were put forth for it. And so they wrote back to us after they saw the results and they said, well, that was just a random sample that you must have got the 28 bad ones. And so I quickly asked them, so how many in your experience have ever failed? And out of, I don't know, the millions they've shipped, they'd only heard about 2 that failed. So they were very confident that they had like a 2 part per million or something like that, or some really, really small probability of failure over the duration we're interested in. And so I did a simple hypergeometric check for what's the chance that if their population was truly that good, that they would randomly sample 28 bad ones out of 30 they picked. And it was one chance in 10 to the 65th power or some number like that. And I wrote to my boss and said, here's the math, here's the results, here's, you know, all my work. I think this is not possible. It's highly unlikely. And he came around the corner and asked, what's it take to be impossible? And so we did not buy those products. You're exactly right, John, is that, yeah, some vendors are a little bit optimistic. And some of it is ignorance of how you're using their product. Some of it is they're just trying to make a sale. They have a lot of incentive to do that. And others don't understand what it means to have a failure mechanism, and there's all kinds of variants of that. So treat the one last quick note on vendor claims. It can work the opposite way too. I was asked to go to a fan vendor that made cooling fans for electronic boxes because they were the best that we knew of. In all of our products that used them, the fans survived much, much longer than most anything else in the box. And one of my colleagues noticed that why are they so good? And just looking at them was really hard to tell. It had some nice materials in it, but it wasn't super fancy versus anything else. It had some decent design, but it was nothing that we could tell that would be the difference. So I got asked to go figure out how do they design it so that they make a really good fan. And the general manager showed me all these data sheets, and every single one of the data sheets had 50,000 hour MTBF on it as their claim for its reliability. Their reliability was way better than that. But it became clear to me that they had absolutely no idea how good their products were. And I bit my tongue. My boss told me not to tip it off because they'll raise the prices on it. But they were already a bit more expensive than other options. Yet their product testing was put it in free air and keep it running and until the bearings basically were absolutely totally gone and the fan mechanism of the motor just fell out. That was their definition of failure. So no back pressure, no start stop cycles, nothing like that. And even then they only had 1 or 2 samples and they would run it for years and say, oh, see, it's good. And so the conditions, there was no accelerated testing, there was no stress conditions whatsoever. It wasn't even close to reality. Yet their engineers said, the senior engineer was, I've been designing fans for years, and I pay attention to this, and this. And everything else is okay, so I can make the cost targets, but these things are critical for it to work. And it was really based on alignment and balance and the best bearings he could get. And they just worked. But the ability of the company to say they were designing for reliability was hinged on or depended on that one engineer's knowledge of how to design a good one. Now, whether he lucked into it or did the due diligence to figure it out, I don't know. But it was clear that as long as that person was there, they were going to create good fans. But their claims on their data sheet were just ludicrous, and their support for it was even worse. So be very, very careful. What I almost always do with vendors, and I highly recommend it, is ask them, how will it fail? If they can't answer that, look for a different vendor. The second question is, how do you know? What evidence do you have for this? If they can't describe the failure mechanisms and the physics, chemistry, and the mechanism itself, well, you might want to work with them to help them understand their own product. The third part is, what evidence do you have? It's not, did you do a test? What evidence do you have? It might be a model, it might be a test, it might be field data, it might be what, but how are they putting together the information that supports their claims? And I really shy away from anybody that says, oh, we've never heard anything from the field. And then I actually did this one day. I said, okay, great. I'll call you back in an hour. And I got on their helpline, their customer service line. It was the worst I'd ever been to. After an hour of trying to get to somebody, hold, disconnected, hold. I called the general manager back and said, I know why you don't get any complaints. You've made it so difficult for anybody to complain. They would rather buy your competitor's product. So you just lose customers quietly, and that's okay with you. That's, but he didn't like hearing that. This one, I hope you already know. Don't do this. Don't do parts count prediction. Chris Jackson believes it has some merit in some isolated circumstances. I get that. But in order for the parts count prediction is not a replacement for an accelerated life test, right? It's not your product. It's not your conditions. It's not based on failure mechanisms. Because so the tally for, say, a multi-layer ceramic capacitor has a failure rate. And that's for any kind of failure that can occur to that component. How are you, what? This doesn't make any sense whatsoever. So please, one, never use parts count prediction. Two, if it's a condition of sale, that's a caveat. You have to do it, but don't use it to make any decisions. And then three, I don't read French, so I didn't read the front matter of the French parts count prediction one, but the English one, the British one, and the US types of parts count prediction manuals or procedures always say something that the prediction as a result of this process is not a reflection of how it works in the real world. And so I'm like, why would anybody do this? But that's a subject for another rant some other day. So why do we do ALT? It costs us money. It takes time. Sometimes we're lucky we can accelerate quick enough. Sometimes we have customers and development processes that are long enough. Sometimes we do it offline before we bring it into the product development. Richard, I'd have to look it up, but there was a paper, and you're asking a question about what standard for parts count. So I remember a paper. It was a British university professor, had a bunch of his students compare the British one, the French one, the Japanese one, and two of the US ones. I think Telcordia and Mill Standard 217, with a product, a small electronics product that they could do a prediction on. And I know that, I think I know where that paper is. I'll make a note, Rich, and I'll send it to you if I get a chance to look it up. But what made that paper interesting was that, so he had all of his students do a prediction, and they broke up, and some did the Japanese one, some did the different 5 ones they had, and they had like 5 or 6 students do each one. They all came up with different answers, even if the 5 were all using the same standard. They had to do it on their own, but they all came up with different answers for what the predicted reliability was. And then they had really good field data. This was a type of product that had pretty much 100% tracking through its lifetime. So they had a pretty decent idea of when it failed and how. And so out of all of these predictions, and say 40 or 50 predictions by different people using these 5 standards, it was minus 400%, no, minus 200% to plus 400% was one of the values that showed in it. They were over in predicting or under predicting orders of magnitude. And one of them got close. And with that many predictions, you'd figure one of them by chance would get close. But there was nothing special about what made that one work versus not work. And the other 4 people with that same group argued incessantly about how to actually do the prediction. So yeah, 2025, you're making me sound old here, Rich. There was a 600% difference. Yeah, and it reinforces the idea that parts count predictions is not worth the paper it's printed on. The paper would be insulted by that comment, I imagine. It is just a random number generator, in my opinion. All right, so what do we do instead? Physics of failure. Understand the failure mechanism, right? Some materials and some systems and some technologies have really good models out there. Some don't. If it doesn't, and it's really important to you, you might be able to create or find a decent model in the literature or by prior work, and build it out from there. It's not for the faint of heart. It takes time. If you really know that this material technologies is going to be key to your product, well, then start that process earlier. You might be able to do the modeling and get a decent answer, or use existing answers that will give you a good enough answer that you can, based on a good, solid understanding of the mechanism and your environment and stresses involved, it may give you enough of an answer that you can move forward and make a decision based on reality to the best extent you have available at the time. If there's no model out there, that's oftentimes when we're pushed into doing an accelerated life test to create a model. And it might not be based on first principles, it may be just empirical. Yet, I think physics of failure, when it's a good, solid understanding of the mechanism and how the various stresses affect that mechanism, is the best way to go. If you want to confirm that model and run a test, it gives you an option sometimes. If you have a solid model, you may be able to design an accelerated test that is aimed at confirming the model versus creating one. And it takes less time and it takes less effort to do it. Not always, your mileage may vary, but starting with a good solid model and a good deep understanding of the mechanisms will allow you to apply stresses in a meaningful way, and with enough samples, being able to say, yes, this model is holding true, and here's the evidence in a reasonable fashion. Just running a test and hoping that you have an activation energy that makes sense is pretty darn meaningless. Yeah, there's a discussion going on with all the various standards out there for, yeah, just don't use them. Go get the understanding as best as possible in first principles. Lots and lots of materials have reliability related standards or papers written about them. And so I often go to those just to look for, how do I stress this? What are the types of mechanisms? How do they react to different stresses? And then from there, it's comparing that to your use conditions and sussing out or sorting out with what you know about the mechanisms, is you can create a rational argument that says we're in trouble or we're good to go, or sometimes in that gray area, well, you go, maybe it'll work. And then we're back to trying to have to design an accelerated test. But now we know a lot more about what's going on. It might be a little easier. The other one, and I find so many people that seem to underestimate this, and then they say, well, we could use field data, but they've spent the last 20 years ignoring field data and not collecting it, not doing failure analysis, and not understanding how their products fail. Instead, handing it off or blaming manufacturing or blaming vendors. It does take an investment and it takes some forethought. So the value of field failures is that it tells you how your product fails in your customer's environment. That is gold, absolute gold. Treat it as an expense or a hit to warranty, or customers always complain, is going to really fuddle up your, that's not really a word, I guess, but it's going to mess up your data. So if you're only tracking how much money you spend and not how many events occurred or what kind of part of the system failed or anything like that, the field data becomes not all that useful. At one point, when I was first at Hewlett Packard, many of the higher end servers and higher end test and measurement equipment did 100% root cause analysis to the component level for all of those products in those divisions. So they had excellent field data. And when they would design, say, a new test and measurement equipment, and they were adding a new feature to it, 99% of the box was exactly the same as it used to be. And so changing small parts of it they could focus their work on that one change or that area that was changed and get reasonable estimates. But it was built on that most of the box was exactly the same. And they also got good at looking at, well, does this increase the temperature? Is this change the vibration? Is this influence the airflow? But their ability to use field data to estimate the future performance of that product worked marvelously. And they they were also the ones that were doing this. Let's do the characterization of life of these new systems, new technologies before we put it in the product pipeline. So if you haven't paid attention to field data as an organization and get reasonable, good information that we could use to say, fill out a block diagram or do an estimate of time to failure for a particular technology, you're kind of wasting a really valuable resource. Now, of course, different industries and different markets vary dramatically. Yet the starting today to get good field data, meaning that it's to the failure mechanism as best as you can get, or at least to the component, or worse, to the module. But heavens forsake, don't say, well, it just failed and it's a stack of servers, for example. Well, what failed? It's not useful at all for us. Invest in it over the long term. It doesn't cost all that much, and you get amazingly good data that you can use to make design decisions, to improve your product's performance, to justify claims on your data sheets, all kinds of stuff. If the data is just pretty flaky, then you're out. You have to start over. But get started on it. It's a really good way to go about doing it. The other one, and this one comes into play when a client or a customer says, well, we've got this box and we want to know if it's going to last the 5 years that we want it to last. Okay, what's your plan? Well, we want to do an accelerated life test. So we're going to take a dozen of these boxes, which will fit into a chamber, and we'll use this temperature to accelerate it according to Arrhenius. Okay, that's fine. If, this great big if, temperature has anything to do with how your product is going to fail in the real world. So let's go look at how your products has failed during the development, all your prototypes. Let's go look at your previous product, if you have one, how it failed. And what are the types of mechanisms that you are suspecting actually occurred or know have actually occurred. And one of them was, there was a product that had to be, it was a 2-person lift to get it installed into a home. And the most common failure in the first month was that there's casters underneath it, that they moving it across stairs or transoms would crack the attachment of the wheel, the tire, basically wheel, to the chassis. The chassis wasn't strong enough to take bumps and shocks and stuff like that. And they wanted to use temperature to accelerate it. Like, a shock loading, yeah, if you change the temperature, the chance of failure will probably change, but not in a meaningful way. This is just the shock loading. You know, if you get past the yield strength of this thing, it's going to crack or it's going to break. And that's it. And most of them, the ones we saw, were seriously overloaded. They probably dropped it from 2 feet onto the stairs of the road. But once they knew the cause, they were trying to design out and understand it. And the mechanical engineers were, doing what they could to come up with, they had like 3 or 4 different designs that would beef up this part of their system, this chassis part of their system. And so we put them in a head-to-head competition. Which ones could effectively survive in like a halt test? Which ones could survive increasing loads of drop at various angles? And there was a clear winner, and they went with that, and they were off and running. We didn't really need to know if it would last for 20 years or not. It was a 1-month experience from them, is that those things typically failed on their first or second installation. And so by creating a system that would help us decide on the best design was a quick, easy way to go. And the other end of that spectrum for that product was a compressor that wore out, and it was a wear mechanism. And so that one we needed to run. And again, they wanted to just put it in temperature to see what happens. And we were able to find an element modeling showed that increase in the temperature of this device actually opened up the clearances where the wear mechanisms were actually occurring, such that they had very light amounts of wear if you increase the temperature. The product actually, for this specific mechanism, got better if you kept it hot. Now, there was plenty of other parts of the system that got much, much worse. So there wasn't really a valuable thing to do in the product design. Yet it pretty quickly showed that the test itself was not going to give them the answer. So the alternative I'm suggesting here is that when you got a big box type thing and you need to know how long it lasts, and let's say there's power supply and a motherboard and a handful of other components in there, compressor, for example, which mechanisms are the life limiting ones for this product? Which specific elements or components or materials is the problem? Sometimes you can accelerate a product at a component or material level easier and faster than at the entire system level. Think of the old spinning hard drives, right? If I was looking at a vibration test, and vibration was important to mechanical wear of some components, and think of the electrolytic capacitors that are hanging out there. If they get vibration, those metal leads tend to crack and fall and break with enough vibration, and is often a concern for transportation type stuff. But some applications do have a lot of vibration, and it was a common way to investigate it. Just increasing the temperature is not going to help us. So once you understand the mechanism at the specific level, I could put 100 capacitors on a bed and solder them down in the way they were going to be soldered in the product without the expense of all the other parts of the system, including that spinning hard drive, which if I got above 5 GRMS, the hard drive would fail. I already know that. I know you don't vibrate hard drives, especially when you're trying to run them. So let's not use the hard drive. Let's use just the component that we're most concerned about. And it may give you a couple of options to improve your ability to get to meaningful results when you put it back in aggregate with what you know about the rest of the system. So bottom line is, sorry about the late start and getting my sound to work and stuff like that. Will this work? Or you always have to do the accelerated test and just crank up the heat? Hopefully not. Please don't do parts count predictions, that kind of stuff. Yeah. Sebastian's talking about our product is rather unique, so field data was critical to the improvement. So good. It can be so valuable in so many different ways if you invest in getting a decent round of that. Yeah, and Carlos talking about this is also a trend for validation tests and combine similarity heritage returns from the field with new testing deltas. Yep, it's a common procedure, yet you need to think it through pretty hard to, especially so you don't miss how interactions behave. So the classic one is if you're going to change just the CPU, but now it's going to kick out 20 degrees more Celsius heat out of it, that may have an effect on other parts of your system. So, focusing on just the one component is the caveat is you got to look at the interfaces and the interactions it may have with other parts. Yeah, good test data, good field data is good stuff. You're very welcome, Mike. Have a good rest of your day. Let's see. Yeah, and Bert mentions that, and speaking of reliability, episode 811, Diana and I talked about predictions. Yeah, we kind of trashed it a little bit there. Yeah, and Michael, it's an issue with field data of going underreported or unreported. it really varies by industry and price point and stuff like that. Um, Alternatives, especially when you're not, you're not getting enough data, is to do buybacks, is to, contact some of your customers and buy back their product, swap it out for a new one for them, because it allows you then to take it apart and see how it's managing, how it's wearing out, how it's failing, and get some evidence that way. Let's see, Samantha's asking, how can one determine the relevance of data to your specific use case? Well, sometimes it's easier than others. Some papers, some organizations actually do the due diligence, saying we are trying to understand how our product is going to be used. And my favorite was an IGBT vendor that said, if you use it in high frequency, here's the model, here's the evidence, here's how to adapt it to your use conditions, and here's the range that we know it's useful, that this is valid for. And if you're in a lower frequency application, there's a different failure mechanisms. Here's the data, here's the model, here's the use applications and range that it's useful for. In some highly technical papers, say just on a polymer, it's really connecting what failure mechanism at the chemistry level that they were investigating, and is that the same in your application? So if you, like in the case when I was working with polymers, we doped it up with all kinds of other stuff. So it really behaved differently, especially after we cross-linked it, than the bulk material would ever do. So the evidence on bulk material really didn't apply to cross-linked material. So we had to look for papers that dealt with cross-linking and the reliability works of it. So once again, I think the heart of all this is really getting a deep understanding of your mechanisms. And yeah, sometimes it takes talking to a PhD. No offense to those out there that are, but you got to understand it. And it allows you then to justify meaningful results, whichever method you're using. Let's see if there are other questions I missed. Joanne is asking, do you guys have a database of failure modes? It's come up over the last year or so, and it's on my, wish list of things to get around to, is to create one. Because we know about lots of ways things corrode. We know lots of ways that things crack or creep or have fatigue failures. We know about thermal cycling related failures. We know about electrical related failures. We know stuff on CPUs or on ASICs. Yeah, we know a lot of different ways things can fail, but there's not one source I know of that gives you a decent repository of. So if you walk in and you have a gold flash coated material, what are the ways that could fail? And it could be production related, it could be wear related, it could be just its technology that it's just not useful or whatever. But no, it's on my list, John, to put something together. Probably not this year. I've got a couple others I need to work on.